Hello, it's Keith here, and this is lesson 6, and this is the final lesson of my IBM370 assembly programming tutorials. Lesson 6, we're going to be looking at the decimal mode. Decimal means binary coded decimal, essentially. So this is where we pretty much use one nibble per digit, and so each nibble, although it should contain 0 to 15, actually contains 0 to 9. Now, on the IBM370, binary coded decimal works slightly differently to the systems I'm used to, at least. Now, we have packed and unpacked binary coded decimal, which packed means that there's a digit in the high and low nibbles of a byte, whereas unpacked just means there's a single digit in each byte. However, the slightly unusual thing, but nothing wrong with it, is that the final nibble within a sequence will actually contain the sign. So if you think of your nibble as containing these bits here, then 1 to 9 is these values here, which of course would match the hexadecimal values as well. But then A, B, C, D, E and F have other purposes. Now A and B, I believe, are if the processor is working in ASCII mode, which it won't be for our examples, we'll be using EBDIC. But that is A would be a positive sign in ASCII, B would be a negative sign in ASCII, C would be a positive sign in EBDIC, and D will be a negative sign in EBDIC. And then E and F, I believe, are just sort of hard-coded to positive. Now, we do need to provide a sign for our binary coded decimal sequences, because if you don't put one in, it probably won't be recognized as being valid, and you won't have things won't work right. So this is something we'll see. As I say, in my previous experience of binary coded decimal, which I'll admit is relatively limited, this was a little bit of a surprise. Now, another thing that was a little bit of a surprise when I was reading the documentation, and it's actually nothing to be worried about at all, is the terms zones and numerics, which sound all kind of spooky and complicated, and they're not. Very simply, in unpacked mode, where each byte only contains a single digit, the digit is the low nibble, and that is known as the numeric. So the bottom 4 bits of the byte are the numeric. The top 4 bits are the zone. Now, what does the zone actually mean? Well, if you look at EBDIC, the zone is actually just the offset to make that into an EBDIC digit, usually. So here is your EBDIC, and here you can see 0 to 9. So to convert 0 to 9 to valid digits, the zone would simply be F. As I say, it sounds very technical, but that's really all it means. The zone is the top nibble, the numeric is the bottom nibble. Overly technical, and as I say, it really comes down to if we are converting packed data into unpacked or zoned data. We do need to sort of just understand that. Now, the one slightly interesting thing is the position of the sign. Now, the sign is always the last nibble with packed data. So if we had 4 bytes, that would give 7 digits, because the eighth, what might be a digit, is actually the sign. In zoned data or unpacked data, it's actually held in the top nibble of the last digit, so replacing the zone. I don't quite understand that. If the purpose of zoned format is to allow it to be easily displayed, putting the sign there doesn't allow it to be easily displayed, but whatever. That is the way it works, so that's what we have to deal with. Anyway, let's go over to our assembler, and let's actually make a start. Okay, so first of all, we have to start up our simulator emulator, and we have to pray to the gods of IBM that everything's in a good mood. So we're going to run this hello, and we will change the text so we can see it works, and we will change it to I like EBDIC, which will hopefully please IBM and make the emulator run okay. So we need to select Hercules job. This is a complete job file, a JCL file. So with my scripts, Hercules job is the one we want to run. If you've got your own scripts, run whatever your own scripts require. Okay, it's off screen, but our emulator is starting up, and I've got some send key scripts to basically start up the server and bypass all of the prompts of the screen. So I'm just leaving well alone and watching it plod away in its own merry little way. And I think we're about to get, oh, there we go, we've got some output here, and we've got I like EBDIC in there, so we obviously have a running server. So there is the console screen. We don't need to use that. That's terminal emulator, we don't need that. That's our server screen, we don't need that either. Let's just get them right off the screen so we don't have to stare at them again. It's this this printer output effectively that we actually want to look at for our examples. Okay, and so this time we're going to run lesson 6. We've got a jump block at the start for our various tests, and the first one we're going to run is test convert. Okay, so we need to this time select Hercules job basic head foot, and we need to run this here, and that will that function basically adds a header and footer that converts this into a complete job, including my debugging tools like this fine mem dumper here and this fine monitor here and my fine humble talk about my own code, which actually isn't that good if I'm honest. But anyway, enough sarcasm aside, let's look at the actual code that we're going to be looking at today. So first of all, we're going to be looking at converting. So we've got sort of two terms. We've got binary, which is the sort of raw data as it is in our registers in every other lesson, and we've got decimal mode, which is binary coded decimal, which will be sequences of data held in memory. So here is some binary coded decimal, and you can tell usually that it's binary coded decimal because it will end in a C or a D like this. So you can see these are two 8-byte sequences here. So to convert a value into a normal binary value, we can use CVB to convert, and so we specify the address of the sequence we want to convert here, and that is the first one. That is this first line here. And our destination here is R0, and then we're doing the same and converting to R1. Now the addressing mode here is the same as every other time in IBM370. So R0 is a hardwired 0 here, so it's not actually functioning as part of the results here. Now we're showing on screen here the results, so you can see here the sequences in memory here, and then we're dumping the registers to the screen. So how are we going to test this? Well, I think we need the calculator. So let's fire up the calculator here. And let's type in 1, 2, 3, 4, 5, 6, 7, 8, 00 here. 1, 2, 3, 4, 5, 6, 7, 8, 00 here. And you can see that we have the value 4960278. So that is the binary equivalent of the decimal value that you saw here, 1, 2, 3, 4, 5, 6, 7, 8 positive. And you can see here you've got that value just there. So that value there is the binary equivalent of the decimal value. Now the second example, we had that value in negative. So the negative version, which is this version here, that D at the end is the negative sign, remember. I mentioned that before. You see here that D is the EBDIC minus sign, and so that is a negative number, and we've loaded that into R1 here. If we look at R1, you can see we've got the value B669FD88, and you can see on our calculator here B669FD88 here. So that has indeed been converted there. So that's all worked as we might expect. So there we've converted a decimal number in memory into a binary number in our registers. We also have the CVD command, which converts a binary value in a register to a decimal in memory. Now the syntax is sort of reversed here. The source is on the left and the destination's on the right, which is the opposite of what we often have, but that's the way this one works. So what we're doing here is we are taking a 32-bit value in our registers and converting it into an 8-byte sequence in memory here, and so we're using offsets 24 and 32 here, and we've got basically the same values in registers R0 and R1 as we started with, and so basically we're just converting these straight back again, and so we're very easy to confirm these have worked. You can see that the same values are now in the memory addresses at the bottom here, and these were previously blank before, of course, and so that's offsets 24 and 32 there, so we've converted those back into decimal there. So that's how we can do that. So that's how we can convert our values as we require. So that's where we've got our values in as sort of hexadecimal numbers in our registers, and we want to convert them into decimal numbers. Now the other kind of conversion we will want to do is packing and unpacking. Now if you remember, packed is what I just showed you, where we have 2 digits in a single byte in the high and low nibble, and unpacked or zoned is where the numbers are in the low nibble and the top nibble is this so-called zone, which we will have as an F if we are using an EBDIC number. So we've got a value here, 1, 2, 3, 4, 5, 6, 7, 8, 00 positive there, and we're basically taking that here and we're then going to unpack that to offset 16. So that's this unpack command. So as I say, the destination's on the left, the source is on the right here. So here is the starting position. We've only got that single value there, and then we're unpacking that to offset 16. So if we take a look at offset 16, well, you can see here we've effectively doubled the size of that sequence. We did specify the length of the sequence. We specified the source as being 8 bytes here and the destination being 16 bytes here. And you know, we would expect the length to double, because rather than storing 2 digits per byte, we're storing just 1. So you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 00, with 5 preceding zeros here, has become F0, 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 F1, F2, F3, F4, F5, F6, F7, F8, F0, and then C0. Now the C here is the C that is here, and that 0 there has been moved to that 0 there, and that 0 there has been moved to that 0 there, that 0 there. And as I say, the I don't quite understand. I mean, it makes sense from an efficiency point of view, but unpacked is, you know, typically designed for showing data to the screen. So I'm slightly surprised that that C0 that C is there in the zone area, because that's not, I don't think, a valid EBDIC value. I guess we could all in the F there for the last digit. I guess maybe that's the point. I don't quite understand it, but anyway, that is how it works. So there we've unpacked our 8 digits to 16 unpacked digits, and then we're using the pack command here, and we're effectively reversing that. We're taking the 16 unpacked digits here, and we're then packing them to 8 digits here. And so again, if we look further down here, you can see here we've repacked those, and of course, well, we end up with the exact same value we started with, because we've just done the opposite command again. So there we go. So that's how we can convert packed data, which is more efficient for storage, into unpacked data, which is more efficient for viewing. Now, in the vast majority of cases, it's going to be packed data we want for actually working with the data in memory. All of the commands like the addition and subtraction and things, they're going to really expect packed data. So it's going to be packed data we generally want to use. Now, with regards to numerics and zones, which are of course only exist with regards to packed data, we do have some special commands to work with them. And you know, I mean, to be honest, when I see these, I kind of think that they might be useful for other purposes, because what we've effectively got here is a command that copies the low nibble of a sequence of bytes, and a separate command that copies the high nibble of a sequence of bytes. And so, you know, maybe you want to use these for things other than working with decimal values or something. Anyway, so what we're doing here is we're copying a sequence of numerics. So here we're specifying the source here. Here we're specifying the destination. And of course, we're specifying just a single length here, because the number of numerics from the source is being copied to the destination. It's the same number in each case. So MVN is move numerics, MVZ is move zones. Here is our starting value. 1, 2, 3, 4, 5, 6, 7, 8, F0, F1, F, and C3. Now, we knew the move numerics, and we moved to offset 8. And so if we look at offset 8, well, you can see that the top nibble in all those cases is stayed 0. It was 0 before, so it stayed 0. And you can see that the bottom nibble of each of those bytes has been transferred across. Now, that was move numerics. And then here we've got move zones. And you can see here, well, the opposite has happened. The top nibble has been moved. The bottom nibble has been left unchanged. Now, what I'm going to do now is I'm going to do something slightly cheeky. What I'm going to do is I'm going to change this C3 to an O3, and we're going to run again, and we're going to see what happens. Now, what have I actually done? Well, that is not a valid sign digit here. And so the question is, how does this actually respond? In some cases, if we change the bottom nibble to a non-valid sign, the commands will actually fail, because they'll realize that it's not a valid numeric decimal value, and it will reject it. But in this case, it looks like it's actually worked. So this command, as I say, it would actually be, for me at least, be potentially more useful for actually manipulating the top and bottom nibbles of data, rather than actually working with binary coded decimal, which I don't tend to do. I mean, just earlier today I was working on a program that was playing 4-bit wave samples, and so you're having to work with high and low nibbles in that kind of thing. And as I say, if you were needing to convert data, maybe this could be useful for that. Anyway, as I say, interesting command there, potentially useful. So there we've really just looked at the various ways we might want to convert data. Now we're going to actually look at some proper mathematics. So let's take a look. So what kind of mathematics have we got? Well, first of all, we're going to look at the simple stuff. We've got an add AP. AP is of course add packed. SP is subtract packed. And CP is compare packed. Now this of course does does raise a very obvious point, and that is that we're really being expected to work in packed data at all times. So you know, we might need to use that unpack command to get things into to EBDIC to show to the screen, but up until that point we're going to be working pretty much entirely in packed data. Anyway, of course all of these are going to be in memory, so we've got our test values here. We've got this this value here, which is a positive number. We've got this value here, which is the value +1. We've got value here +2, and then here we've got a 0 value, but we do have to put a sign at the end, as I say, otherwise we might annoy the IBM370 because it will not recognize these as valid numbers. Okay, so what are we going to do first? Well, what we're going to do here is we are going to add the value at offset 8 to the value at offset 0. So effectively we are going to add this value here to the top value here. And then what we've done here is we've done the addition of 8 bytes at offset 8 to the 8 bytes at offset 0. And we're specifying the length of our decimal numbers in each case here because there isn't a requirement for them to be the same length. And of course there could be wildly different lengths. So we can see the results here. We started with lots of 9s and an 8, and we added 1, and so we ended up with lots of 9s and a 9 here. Now after that we were very unexciting. We simply subtracted the same value here. So then we went from 9999999 to 9999998 here, and that's we added and then subtracted the same value. So quite boring there, really. Anyway, so that's what we've done there. Now what we're going to do next is we're going to use the compare command, which works in a very similar way, really. Nothing particularly remarkable here. So what we're going to do here is we're going to repeatedly add our value of decimal 1 here at offset 8 to our test value, that very high number here. And we are going to then compare it to the value at offset 16 here. Now the value at 16 here, we've got a 1 here, and then we've got a 2 here. So this is a sort of high number, a few along from this. And so we're comparing to that, and we're going to repeat until we reach that value. And so you can see here that we've started from at 9999999, then we've gone to 1 and loads of zeros, 1 and 2, and then at that point we've ended, because that not equals command will have looped until we matched that second value at offset 16 here. Now of course if the value here was different, we would have continued that loop for longer, although we don't want to continue it for too long. We might overload our printout there. So that's what we can do there. Now that's a simple addition and subtraction and comparison, but we go even further with the binary coded decimal on the IBM, and we actually have a multiply command and a divide command. We're going to basically multiply D1 by D2 and store the result in D1. There is a requirement that D2 must be a smaller number and must be shorter in length. So we're specifying 2 lengths, and the second length must be lower, so that length is 4 there, and the first length is 8 there. So that's how we're fulfilling that. Now our first value is here, so that value there, and our second value we're just using this second part here, this 4-byte value here, and so we're going to do that. And of course the result is going to be stored here, and we've got a nice easy value there that we can easily see that multiplication has occurred. So here is our command, and I'm just waiting for our emulator to run the command. Okay, so the multiplication has now occurred. So here was our starting position here. So we multiplied 100002 by 123, both positive numbers, and we end up with 123,000,246C, as C being positive of course, and so that has clearly worked. So that is our multiplication there. We're then going to do a division with DP, divide packed of course. Now in this case L2 must be shorter than L1. Now this is a little bit tricky though, because the result in the destination here is split into 2 parts. Now the least significant bytes, in this case 4, the L2 bytes, the bytes of the second parameter, are actually the remainder part of the result. And so in this case the top 4 bytes will be the whole number result, and the bottom 4 bytes, the least significant 4 bytes, will be the remainder. Well, this of course will be clearer when we see it on screen. So we started with this value here, 1 2 3 4 5 6 7 8, and we divided by 1 and then 3 zeros. Now our second value was 4 bytes. And so these 4 bytes here are the remainder. So 678 was the remainder. And then the whole number part was this part here. So 1, 2, 3, 4, 5. You can actually most clearly see the separation there because you've got the C, which is the plus sign there, and the C, that's the plus sign there. So you can see there are 2 parts there. However, the separation is simply defined by that second value. If we change that second value and we change that to a 2-byte value, for example, if I change this here and I change this to 2 and I change this to 30 and I run this again, well, now you can see that that is now the remainder, and that is now the whole number result. It's the length of the second parameter that defines how much of the result is the remainder, which is a little bit of a pain, but of course it makes logical sense from the point of view of producing the correct result and using the memory most efficiently. The remainder is only going to be the length of the second parameter or less, so it makes sense. Those are the sort of addition and subtraction multiplication commands. There's a few other slightly more obscure maths commands that are definitely worth discussing though. The first of these is very obscurely titled. It's called zap, which sounds like we have to get our ray gun out. We do not though. What it actually means is zero and add packed decimal, which also sounds a bit crazy. It simply is basically moving a value and changing its length. It's adding to 0, and so the result is just the value that was passed in. But the point is the length can be changed. So what we're effectively doing is taking our 4-byte value here and converting it to an 8-byte value at the offset 8 here. So if we look at this and we fire this up, we'll see this in action. So here we had our 4-byte value here, and we've filled the entire memory range with F there, so we can clearly see it. There's our 4 bytes. So we've 0 and added that to the offset 8, and we've converted it to 8 bytes. And so you can see here, we now have this 8-byte value here that is the equivalent of those 4 there. Now the other bytes at the bottom there have been done by the other command we're looking at, and this is MVO. Now this is move with 4-bit left offset. So this is a bit like a rotation command. It's not quite because it actually copies the data, but this is the closest we have to a rotate command on this processor in decimal mode at least. So sorry, of course it does have rotation commands. It doesn't have them in decimal though. So that's what this is doing. So you can see that every time we run this, we're effectively shifting by 1 digit to the left, 4 bits to the left each time. Now, as I say, it's not quite a rotate command, but that is what it is intended as. So we're shifting by 1 digit. Of course, if we needed to shift by 2 digits, we could literally do a regular copy there. But this shifts by a single digit, so allows for a half-byte offset effectively. So there we go. So that's what that does. Now, those are the last of the maths commands, and now we get to the really crazy command of the IBM370, which in my experience is the most advanced command of any assembly language, of any processor I've come across. I don't know about the silicon. I don't know how much of the silicon was allocated to this, and I don't even know how many of the processors actually had this command. Now what this command is doing is it's effectively a format command. If you're familiar with BASIC or various kinds of programming language like C and things, you'll have these commands that take a value and then they format it to a string, if you will, and you can put commas in and you can say, well, here are the zeros, this is where you have the sign, and that's what this command does. And as I say, this kind of command is very common in BASIC, it's very common in high-level languages. I've never seen anything of this complexity in silicon before, because as I say, this is a processor level command. It is my understanding that some of the IBM processors didn't have the decimal extensions, so not necessarily all of these had this, but the fact that this exists in silicon was really quite shocking to me, to say the least. Now, before we actually look at the results, because they are very complicated, well, the results are very simple, but the way that the results are produced is quite complicated. Well, let's go over to our text screen and let's see the actual contents here. So basically, the way that this works is we pass it two things. We pass it a decimal value, or more than one decimal value, even, because it can do more than one in one go because it is so complicated. And we provide it with a format string, which, as I say, if you're familiar with C# or with BASIC and things, you might be familiar with these. You have hash symbols and full stops and more hash symbols and so on and so forth, and then zeros if you want them to be zero even if there's no value there, and things like that. And that's in a lot of ways what we do with this command. We pass a string that has a sequence of values. Now, I've shown them here as D's and S's and F's, and that is for visual simplicity. These are actually hexadecimal values of 20 for the D, and that is a digit, and so these are digits that may or may not appear. Now the S is the significance start, that's the hexadecimal 21. Now this after this is a digit as well, but what this basically means is the following digits, the following Ds if you will be shown whether there was a preceding digit or not. So in the example of a value of 0, you might want to show 0.00 even if there was no value to show anywhere else. But if there was a value of 1,000, you want to show 1000. So the S defines the start of the 0.00 part, if you will. You'll see it later on. So that's what that does. The F is the field separator. Now this basically allows us to have multiple values on a single line. This is intended, I think, for accounting purposes, because that will be, the IBM370 will have been doing a lot of invoice processing and a lot of accounting kind of stuff, being as it's like a sort of mini computer kind of category. It wasn't a desktop PC, it wasn't a Game Boy, it was a server for batch processing effectively. So that's the kind of thing it would have been doing, and that I think this will be used for accounting purposes. So those are our options, and then we build those together with our string. Now the string actually has a few other things. Now the first character in the string will be processed and will be remembered, and that is used as the filler character. Now that would typically be a space, but for visual convenience, we'll use an underscore, because that allows us to see what's actually going on under the hood, if you will. So then we've got some D's. Now that means they will either be shown or not be shown, depending on if there was a digit to show. We've then got a comma. Now the processor is smart enough to know that if there's been no digit shown yet, that will also not be shown. And so all of these will be replaced with that initial character in the sequence. Okay, so things will continue along. And then we get to the significance marker here, which is shown as an S here. And so this tells the processor, okay, you now need to switch into the alternate mode, which is show things whether there's anything to show or not. So in the case of our 1000 here, we're already showing values, but in the case of our 0.01 here, we weren't. But now that has switched into the significance part, and so the following D is shown as a 0, and the full stop is shown whether it was needed or not, if you will. Because this comma wasn't shown in this example above because there was no digit shown yet, but this full stop is shown because it comes after the significance marker, and that continues until we get to the space here. Now that then switches us into another mode, and this is basically where we are into the positive negative sign area. Now in the case of a positive value, this will be effectively cleared if the value that's being shown is positive. However, if the value being shown is negative, this will actually then be shown as is. So in this case, we're showing a CR for credit. Otherwise, we could show a minus, but you could show I am a fish if you felt like it. As I say, it's not. There's no intelligent processing of what this means. It just knows that the sequence of digits has ended, and so anything else in this position must be relating to the sign and should be hidden in the case of positives or shown in the case of negatives. And so that's what's done. And again, in all of these cases, it's this character here that was at the start of the line that was being used to remove the values that shouldn't be shown. Now, as I say, the D's, S's and F's and things here are all inconvenience. And the F is, I should have said that, sorry. The F here is the field separator. So that is basically saying reset and start again for a second set of values. So two decimal values on each line in this example. So as I say, D, S and F there is just for visual convenience, so we've got something we can read in a single character, but these are actually 20, 21 and 22, DS, SOS and FS. So that's what we have. And as I say, any of the character is processed depending on the position. Okay, so let's go over to our code after that rather long description. And let's see what we've actually got here. So what I've basically done here is I've kind of marked all of these up as best I can. So we've got our D's here, which are 2, 0. We've got our S, which is 2, 1. We've got our F, which is 2, 2. And then we've got various EBDIC values here, I guess. And so, as I say, this is the spacer character here, which is 6D in this case. And what we have to do is we have to provide this in a repeating form for as much data as we're actually going to try and show. And this is the values we're going to show here. So the C's are positive and the D's are negative. So we've got 2 values on each line, so I've put them in the same format. The F is the separator, of course, for the 2 values on each line. And we're going to fill this out here. Okay, so let's fire this up. Well, we have already fired it up, actually. We've already shown it to the screen. So that's what we've got here. And so we're going to show this to the screen. So first of all, what we need to do is we need to use the edit command. We need to specify our length and we need to specify the value we're going to show. Now, first of all, we have actually shown our sequence as a single line before any processing has occurred to the screen. And so that's why you've got this weird line here with these with all these weird characters here that probably should have never been shown to the screen anyway. But that is our kind of template line, if you will, that shows what we had to start with before the edit command took its action. So first of all, we took the decimal value and we processed 23 characters and we processed them from offset R8, which was our pattern, and we specified offset 0 here as the destination here. And so the first 2 decimal values will effectively have been drawn there. And then what we're doing here is we're doing the second 2 values, offset 8. So we're moving 2 values along because we've got 2 values on each line. And we're doing the second line here, 23 characters along 23 lines for the character. And that's producing these results here. So you can see here that this first value, this value here, 11100D, and then followed by 1C here, that first value was negative. And so the negative sign here has been retained, but the second value was positive, and so in that case it's been cleared. And in all cases, when something is cleared, it's always cleared with that first character on the line, this character here. Now we can confirm that if we change that character. So I don't know the characters off the top of my head, so let's try 6C, and we'll probably have something very weird come out indeed. I'm sure it'll be something valid. See what happens. Okay, so we now got crazy percent symbols everywhere. So you can see that everything that's been cleared, including that minus sign in the case of the positive number, has been replaced with that first character on the line. That first character on the line is really the sort of key to it all, so to speak. So there we go. So that's how it works, and as I say, it's very, very advanced. We can have all of these digits. They will fill in where there's values to fill in, or they will clear where there's nothing worth showing. We can have our sign as a minus, or as I showed before in the example here, we can have a CR. We can do whatever we want there. It only shows if it's negative. You can't have like a plus there. If it's positive, I don't know what the rules are when it comes to accounting. I don't know if that is the only way of things. I don't know if it's like verboten for accountants to show a plus sign. Maybe it is. I don't know. But anyway, so that's what this does. Now, as if edit wasn't ridiculously complicated enough, we have an even more advanced version called edit and mark. Now, this one is a little bit more tricky, and I don't think it works very conveniently for 2 values on a line, but basically what it does is it will effectively it will memorize the position of the first non-zero digit within a sequence. It will actually load these into register R1 whether we wanted it to or not. It's one of these commands that where whatever registers we use in our command, R1 takes the value by default. Now, I believe what this is for is to show a currency digit in a position before the first number, but not in a very specific position, because obviously we could show it as the very first character on the line. But if we want it to move around with regards to the other digits on the line. Now, the only limitation here is it doesn't actually set if there was no characters inserted. So we had that significant start, which is where we show values whether there's anything to show or not, and that won't set that register value. It's only if there was a value to set. Now, in the case here, what I've done is I've exploited this, and I'm using this doSim command, And here we're checking if we actually found a character, but otherwise what we're basically doing is we're storing R0, and I'm loading R0 with some mock characters here. So I'm loading the Y symbol because I'm in Japan here, so that's yen, and here we're loading the dollar symbol here. And so what this does, as I say, is it's loading so that we can calculate, it's calculated rather, the position for these symbols here, and they are preceding exactly the first digit that was added. Now, as I say, depending on our value, there may not be a digit added, because in the case of 1, 2, 3 here, the 1 here was after the significance start, so it was basically being loaded in to this position here. So it was after the significance start, and so the editor mark command was not loading R1 in that case with the correct position. Now my code could have my code is checking here to see if R1 wasn't loaded. What I could have actually done is I could have preempted it and loaded in what I knew that position to be, so that if it didn't actually set it to something else like this or this, then we could actually have done it correctly. Now, one thing, I'm actually saying this slightly wrong. It's actually loading that value there or that value there. I'm actually subtracting one before I'm storing my character into the string. But that's what editor mark is doing. It's remembering the position before the sequence. So there we go, a very complicated command indeed. So that's pretty much all we're going to be doing with the IBM 370. I'll be coming back later to do a few very basic, some hello world type of stuff, just as sort of easy content for people who don't want to watch an entire series and just want to see a little bit of IBM 370 to get them started. But basically that's the end of this series. I am planning on covering the IBM 370 in a book I do next year. So by the time this is made public, that book will probably be available. So please check the comments below this video, because I'll update that with a link to the book if you're interested. I hope you've enjoyed this series. I really don't know how many people will view it. For me, it was really... And so I had a family member who programmed this thing, and I actually sort of, by sheer coincidence, I bought a book from a local bookstore that was made about 10 years ago, but for some reason was written originally in the 70s. So I gained a little bit of an interest in it and that, and I found this process to be very interesting just because of its sheer power. As I say, that edit command is one of the most advanced commands I've seen in assembly, so I've enjoyed this and I hope you have as well. Anyway, as I've said before, go and check out some of my other assembly tutorials if you want something else. Thanks for watching today though, and goodbye.